how do we do this thing? I'm just gonna solve the Schrodinger equation right now, and I'm gonna give us an order of operation for solving the Schrodinger equation. Number 1, cry. Number 2, pray. Number 3, guess. And number 4, solve. Cry, pray, guess, solve. That's how we're going to solve the Schrodinger equation. Let's do it. All right. So for now, I'm going to say let's just make our lives a little bit easier. No potential energy. Beautiful. And so that means now we've got negative h bar squared 2m times the second derivative of psi equals E psi x. So we're not going to worry about that potential energy term for now. I want to get this in terms of the reduced equation, which means I want to eliminate the constants in front of the second derivative, and I want to get this whole thing set equal to 0. Okay? So I'm going to write that as second derivative of psi. And I'm going to do a couple of different algebraic steps at once, and I'm going to describe to you what I'm doing. First, I have to subtract that over to make it all equal to 0. Okay? Then I'm going to multiply through negative 2m over h bar squared. And so if you have to pause and do that real quick for yourself, by all means. But I'm going to write that directly as the following. So that becomes my reduced form. So we notice here 2me over h bar squared, that's a constant. We also notice that I don't have a first derivative, but that's okay. It's still a standard second order differential equation. So now I'm gonna guess. So we've cried and we've prayed, and now it's time to guess. So we're gonna guess that psi of x equals e to the ax, and that cannot equal 0, just like I did before. We're going to take the first derivative, d dx of psi of x, and that equals aeax. And then we're going to take the second derivative of psi of x, and that equals a squared eax. Okay? And now I can plug these back into my reduced equation. And that's going to go as the following. Second derivative of psi is a squared e ax plus 2me over h bar squared. And we don't need the first derivative solution in this equation. We needed it to get the second derivative, but we don't need it to write for the reduced form here. So now I can just say 2me over h bar squared times psi, and that is e to the ax, and that all equals 0. So I can eliminate the e to the ax, and I just have simply a squared plus 2me over h bar squared equals 0. And now I can inspect this, and I notice here that I don't need the quadratic to solve this, right? You might not have to use the quadratic, okay? And remember, 2me over h bar, that's all constant, so I'm trying to solve a, right? So a is going to equal negative 2me over h bar squared, and I take the square root of that, and this is going to be imaginary roots, right? Because I have the square root of a negative number. And so I am going to call that, I'm going to call all of this 2me over h bar squared equal to k. So I'm going to say k equals 2me over h bar squared. And so my solution is I times k. Okay? And so because my solution is I times k, that's where I'm going to use sines and cosines. So I can say here directly Oh, you know what? Sorry, k is the square root of all of that stuff. Okay, and you might notice, just really briefly, if I go back for 1 second here, where did we come up with that? Let's see here. Yes, look at that. K equals 2me divided by h bar squared square root. That's where that came from. Okay? So now, because that's a equals ik, I can say psi of x equals, and I'm just going to use a's, b's, and c's, and d's to make life a little more straightforward. So e equals I to the kx plus be to the negative I kx. So that's one form of the wave function I could use. And then, but we know through Euler that it will be more practical to say that this is sine kx plus cosine kx. And I don't want you to worry yourselves for now with these a's, b's, c's, and d's. We will be able to figure out those in time, okay? We're going to solve them through the normalization process. But what's important to note here, all right, we can see that our Schrodinger equation, when we solve it, is made up of waves, of a wave function. Literally, our wave function is made up of sines and cosines, okay? Which makes good sense. All right, folks, I'm sorry that went a little bit longer than I wanted it to. So I'm going to post in the module some example problems, more general example problems of second order diffie-qs and their solutions, just so you can get a hang of this process, okay? All right, I'll see you later.